Hello everyone, welcome back from spring break. Obviously you found the videos, and right above them is a folder with the guided lecture notes, so that's what's displaying in front of us. I made up these notes so that it would streamline the process a little bit, and basically we'll just go through the examples. I'll give commentary as if we're in the normal classroom. So our first topic for exam 3 is integrating powers of trig functions. When we integrate powers of trig functions, basically we have three main considerations. The first is what I always refer to as the basic six, the antiderivatives of the derivatives of the six basic trig functions. If those fail, then we consider the integral of u to the n with respect to u, and choosing u to be the entire one of the trig functions involved if it's not fitting one of the basic six. And then worst case scenario would be trig identities. So here we're going to be exclusively involved with integrating powers of trig functions. So the majority of the time we're going to consider the basic formula for the integral of u to the n, which of course is a power. So we have two main areas, sines and cosines, where there's two cases, and secants and tangents, where there's four cases. And the reason why there's different number of cases is basically because of the nature of their derivatives, as we'll see. Notice we don't have an area for cosecants and cotangents. We could, but we avoid those because the secants and tangents methods are the same as cosecants and cotangents methods, the only difference being negative signs in the derivatives. So to remind us of a Calculus 1 example, we'll first start with integrating powers of sines and cosines. So here's a Calc 1 example. So we have the integral of cosine 3x and sine to the fourth of 3x. So if we're going to try to, it obviously doesn't fit one of the basic six, so the next thing is to consider u to the n. And so we do see one of the trig functions is a power, the sine in particular. So in an attempt to fit the form for u to the n, we'll choose our u to be the sine of 3x. Now remember, you never pick the power, because the power is going to be accommodated in the formula for the integral of u to the n. So then we need to satisfy our du. So du is cosine 3x, don't forget times 3, and differential dx as well. And then we modify by our 3, and we get 1/3 du is cosine of 3x times the differential dx. Now, maybe let me rewrite this off to the side here. So I'll rewrite the original integral cosine 3x sine to the fourth of 3x. And in an attempt to fit the form of u to the n, we had chosen our u to be the sine of 3x, and so we chose our u to be sine of 3x, so sine to the fourth of 3x represents u to the fourth. If we look at our leftovers in the integrand, cosine 3x dx, compare them to our du, and we see they match. So we could replace those by 1/3 du, and then fitting the integrable form, we'll bring out the 1/3 integral u to the fourth with respect to u, and we can then integrate. So the 1/3 tags along, of course. The fourth integrates to be u to the fifth over 5. We'll add our constant of integration at that point. And then finally back substitute, so we get 1/15th, and then our u was sine of 3x, so let's write in shorthand sine to the fifth of 3x, and don't forget our constant, of course. So then the question becomes, what about an integral like this? Let's say cosine cubed of 2x sine to the 6th of 2x. In the Calc 1 example, we were able to choose u to be the sine of 3x, and the du was there automatically being the cosine of 3x. But in this case, if we choose u to be sine of 3x, or excuse me, sine of 2x, there's too many cosines. We only want one. And similarly, if we choose u to be cosine, then there's too many sines. So we need a little strategy. So here's the case 1 strategy when we're integrating what we call odd powers of sines and cosines. First thing is to, and you know, as we talk about the strategy, you might not realize that why we're doing what we're doing, but as we work through the example, I'm sure you will. And it's just a little cookbook recipe. Hopefully, after we do a few examples, you'll get the flow of it, and you won't need to refer back to this, but it's here for you. And what you're going to do is locate the smallest odd power of sine or cosine. And the last examples will show us why it's the smallest odd power that we're concerned with. And then what we do is we take one factor of that smallest odd power and we isolate it with the differential dx. And then, as I wrote here, we're going to save that. And that's going to actually help to satisfy the du in the formula for the integral of u to the n with respect to u. So, in a sense, it's almost like we are reversing the process of u substitution. Instead of choosing our u and making sure the du is satisfied, we're forcing the du to exist. And then here's step 3. We're going to change the rest of the factors of that smallest odd power, which now is even because we borrowed one of them, to the other trig function. If it's sine, change it to cosine. If it's cosine, change it to sine, by our Pythagorean identity. And then I just wrote finish. So let's see how this little strategy works out here. So let's see, I'm going to recopy the integral again. Move that up. So we've got the integral of cosine cubed 2x sine to the 6th of 2x with respect to x. So the smallest odd power, the only odd power, is the cosine. So according to the method, what we're going to do is we're going to take one factor away from cosine cubed. We're left with cosine squared of 2x. We'll recopy the sine to the 6th of 2x. And that factor of cosine 2x that we borrowed, we'll push over with the differential dx. Maybe even go so far as to box it off and write the word save if you like. Because again, the intent is for this cosine now to satisfy the du in the formula for the integral of u to the n with respect to u. So we're going to now convert the remaining factors excuse me, of cosines to sines by the Pythagorean identity. So that's just a simple transposition. We have sine squared theta, not to insult you, plus cosine squared theta is 1. So if we want to solve for cosine squared, that'd be 1 minus sine squared. And so we'll replace cosine squared by 1 minus sine squared of 2x. Recopy sine to the 6th of 2x and the cosine 2x dx that we're saving for our du. And now is the point where we could start the u substitution process. That is, we've forced the du to exist in the form of the cosine of 2x dx, and we've changed everything else to be in terms of a u that would produce it. And that u in particular is the sine of 2x. So at this stage, we'll start the u substitution process, choosing u to be the sine of 2x. Again, we don't pick the power, because the power is accommodated in the formula for the integral of u to the n with respect to u. The du is then calculated. that's cosine 2x dx, but wait a second, times 2. So don't forget that derivative of the argument. Modify, this should be routine. So 1/2 du is cosine 2x dx. Okay, go back to the integral, account for all the factors. Here we have 1 minus u squared, u to the 6th, and then the cosine 2x dx makes up 1/2 du. So, making the change of variables, bring out the 1/2, integral 1 minus u squared, u to the 6th, and the differential du. Now at that point you might be looking at it and saying, okay, well, now I've got a product, and what do I do? Well, because of the nature of these powers, one thing you have to realize is we can only integrate a sum or difference of terms of the form u to the n. And so we can't integrate a product. And because of the nature of these functions and their powers, we'll always be able to do some obvious algebra to get to a point where we can integrate, again, only a sum or difference of terms that are of the form u to the n. So just some natural algebra. In this case, the u to the 6th can be distributed. Okay, so here's all I like to do. I'll leave the 1/2, the integral, distribute the u to the 6th, get u to the 6th minus u to the 8th. And now, with respect to u, of course, and now I have a sum or difference of terms that are of the form u to the n. So we'll integrate. We'll just do it term by term. I'll leave the 1/2, open up a set of brackets. I like the square brackets because that kind of reminds me that I've got to distribute the 1/2, and then just integrate term by term. U to the 6th integrates to u to the 7th over 7. U to the 8th integrates to u to the 9th over 9. Add or constant. And finally distribute 1/2. So 1/18th u to the 7th. 1/14th u to the 7th. Okay, that is 1/14th. Let me fix that. And then we get the minus 1/18th u to the 9th. Now, we're going to see in some examples that we're going to have like maybe 3, 4, 5 terms containing u. So instead of having to back substitute, I'm going to allow you to get away with writing me a little note here telling me what u was. But this has to be included in your final answer, otherwise you're going to lose a point. So basically you have 3 choices. You could write me the note, or you could literally back substitute. So here we'd have another acceptable answer, 1/14th sine to the 7th of 2x minus 1/18th sine to the 9th of 2x. Plus c. So write me the note, literally back substitute, or your third choice would be to lose a point. Okay, so that's the method. Now we'll see some other examples. So on the next page, here's another example at the top of the page there. So we have cosine to the 4th and sine to the 5th. So again, it's the smallest odd power that you want to focus on. And so even though 4 is smaller than 5, 4 obviously is even. So you're going to take one factor of sine away from, actually let me rewrite this first. Okay, So we're going to take one factor of sine, recopy the integral of cosine to the fourth 5x, taking one factor away from sine to the fifth, we're left with sine to the fourth. That factor of sine of 5x push over with the differential dx. Once again, go so far as to box it off and write the word save. Now our intent, once again, is for that factor that we boxed off here to make up our du. So then you could look back at the cookbook recipe if you like, but the logical question to ask would be that if the sine of 5x is going to represent the du, what's the trigonometric function whose derivative gives us the sine of 5x? And we don't have to worry about the constant multiples, negatives, or anything like that, but the substance of the question is, what trig function has a derivative that gives us sine? And that, of course, is cosine. So therefore, if we could change the remaining factors of sines to cosines, we'll be able to start the u substitution process. Now, it was easy in the last example because it was just cosine squared, and so we had the identity immediately. But it turns out that any even power of sine or cosine can be transformed to the other, cosine or sine, by the Pythagorean identity, because consider this. We have the identity that sine squared theta plus cosine squared theta is 1. So if I'm concerned with sine, I'll isolate sine squared theta, it's 1 minus cosine squared theta. But I need sine to the fourth. Well, sine to the fourth can be thought of as taking sine squared and squaring it. Because, of course, you multiply the exponents. So, therefore, that would be equivalent to saying 1 minus cosine squared as a quantity squared. And that would hold for all even powers. For example, if you wanted sine to the sixth, consider sine squared as a quantity cubed, which will give you 1 minus cosine squared as a quantity cubed, and so on. So that's our plan now. Come back to the integral. Cosine to the fourth of 5x rewritten. Sine squared is 1 minus cosine squared, so 1 minus cosine squared of 5x accommodates two factors of sine, but to account for 4 factors, we square that, just as we talked about over here, and then we'll recopy the sine of 5x dx that we're saving for our du. And now's the time where we want to start the u substitution process. Once we get to a point where we've forced the du to exist and we changed everything else to be in terms of the u that produces it, then we start the u substitution process. And we're going to choose u to be the cosine of 5x. Again, never the power. Let me put a little line here so you know that that's from off to the side. Okay, so u is cosine 5x. Never the power. du is, okay, be careful, minus sine 5x, don't forget times 5, differential dx, modify, we get minus 1/5 du is sine of 5x dx. Go back to the integral. Okay, u is cosine, so here's u to the fourth. 1 minus u squared is a quantity squared, and then the sine of 5x dx makes up negative 1/5 du. So notice how all factors are accounted for, change of variables, bring out the negative 1/5, integral u to the fourth, 1 minus u squared, quantity squared, and our differential du. Now, in the last example, we were able to do some algebra by distributing that u to the sixth or whatever it was. In this example, we can't do that here because this quantity is being squared, so that's stopping us. The squared power is stopping us from distributing the u to the fourth. And always remember, you can only integrate a sum or difference of terms of the form u to the n. So what we're going to need to do is just some basic algebra. If you have a binomial squared, obviously you could just FOIL that out. So if you need to, take it off to the side. 1 minus u squared times itself, and then FOIL. Now, in terms of squaring a binomial, there is a shortcut method. You square the first, so 1 squared is 1, 2 times the product, so 2 times 1 times negative u squared, negative 2u squared, and then you square the second, squaring negative u squared, we get positive u to the fourth. So if you like that method, that's great. If not, you're going to distribute, or you're going to FOIL it out like I suggested here off to the side. Okay, looks like we'll try to squeeze this in. Integrating now, not integrating yet, because you have to have a sum or difference of terms of the form u to the n. But now at this point, we can distribute. So u to the fourth is distributed, u to the fourth minus 2u to the sixth plus u to the eighth, all with respect to u. Okay, now we can integrate. Move off to the side here, minus 1/5. Open up a big set of brackets. Integrate term by term. U to the fourth integrates to be u to the fifth over 5, excuse me, minus 2 tags along, u to the sixth integrates to be u to the seventh over 7, and then finally u to the eighth integrates to be u to the ninth over 9. Add our constant, and we'll distribute the negative 1/5. I'm going to leave it in terms of u. Negative 1 over 25, u to the fifth, plus 2 over 35, u to the seventh, and minus 1 over 45, u to the ninth, plus our constant. And remember, if you do leave it in terms of u, write the little note saying what u is. And u was, okay, up here, cosine 5x. Okay, so that's the idea. We'll extend this a little bit further, and in the final few examples, we'll see why we focus on the smallest odd power. To begin with, this power here of the 1 minus u squared, it was just squared, and so we were able to come off to the side and FOIL it out, or use a little shortcut method for squaring a binomial, and then ultimately distribute to get a sum or difference of terms of the form u to the n, so we could integrate. If this is a power of 3 or higher, then the most efficient way to proceed in terms of its expansion is Pascal's triangle and the binomial theorem. So in general, that's used to expand any binomial, a plus or minus b raised to the nth power. And remember the triangle, you start with a 1, first and last entry, and any row is a 1, so you bring down the 1, bring down the 1, and then you get another row with 3 entries, and the middle entry here is obtained by adding the 2 adjacent elements above it. So you bring down the 1, 2, and 1, continuing 1, 1 plus 2, 3, 2 plus 1, 3, bring down the 1, you can go on as long as you like. 1, 3 plus 3 is 4, 3 plus 3 is 6, 3 plus 1, 4, bring down the 1. I'll just go to the 5th row. I doubt we'll ever get anything higher than that. And that's 1, 5, 10, 10, 5, and 1. But you could go further if you wanted to. Now, the significance of this is that it gives us the coefficients of the terms in the expansion. And one thing to note is that the second entry in any one row tells us the power that we're raising the binomial to. So, for example, well, I guess these are the trivial ones. N equals 0, n equals 1. Okay, here starts what I was talking about. N equals 2. Notice it's 1, 2, 1. And look back up here. When I expanded this with the shortcut method, that was the coefficients. 1, 2, and 1. So then n equals 3. And again, it's the second entry. Tells you the power that you're raising the binomial to. Okay, so before we incorporate this within the context of a integral problem, let's just practice. There's a couple things I didn't mention. You could expand this any way you want, but here's the easiest way. So I'll create the triangle off to the side. It's the fourth power, so 1, 3, 3, 1, 1, 4, 6, 4, 1. So that's what I'm looking for. I'm going to spread out the coefficients. So 1, leave some space. 4, leave space. 6, space. 4, space, and 1. Now the next thing we'll do is we'll account for the signs of the terms in the expansion. And you have two choices. Either the signs are all positive or they alternate. And if this is a negative, the sign between the two terms in the binomial, then the signs of the terms in the expansion will alternate sign, always starting positive. So positive, negative, positive, negative, positive. Again, the only other choice is if they're all positive, and that would be if this is a sum between the two terms, because there's no way to generate a negative. And then to account for the powers of the terms in this expansion, you start with the highest power, or you start with the first term of the binomial, 1, raised to the nth power, in this case the fourth, and the second term of the binomial, u squared, raised to the 0 power. And then in each subsequent term of the expansion, you decrease the power on the first while you increase the power on the second. So 1 is cubed, u squared to the first. 1 is squared, decrease. U squared squared, increase. 1 to the first. U squared cubed, and finally 1 to the 0, and u squared to the fourth. And then really what comes out of this essentially is just the coefficients and the powers of the u's. So these guys are all 1s. 1 minus 4, u squared to the first, u squared, plus 6, u squared squared, u to the fourth, minus 4, u squared cubed, u to the sixth, and then finally plus u squared to the fourth, or u to the eighth. Okay, so that's all we expand, and go to the next example. So we've got two examples to finish up this topic. And the next one is sine to the 7th, cosine to the 11th. Both arguments are 3x. Okay, so this is going to be the short way. This will illustrate why we have a we want to focus on the smallest odd power.